Hey, this is Horner, and this is my version of Giambattista's Chapter 2 that talks all about force. Um, Interactions and forces is the first section, and we're going to be studying a topic or a subtopic of physics called mechanics. And basically, all mechanics says is that if you use a force, you'll affect the motion of an object, or in order to get something moving, you have to use a force. A force is defined very easily as just as a push or a pull. So if you think about a car, you can either pull on the car to get it to move, or you can push on that car, either a big car or a little toy car. And there's two types of forces. There are contact forces, and then there's long range forces. So we can look at both of them here. The contact force basically is the gentleman here kicking the ball. So when his foot is touching the ball, then that is what we call a contact force. After the ball is no longer touching his foot, then there is a force due to gravity. And we will talk about why this is F with a little g here. But that's a long range force. There's no contact between the ball and the earth, but there still is a force affecting the ball from the earth. We simply call that force of the earth on any object the gravitational force. And we think about it as weight. And we'll talk about the difference between weight and mass as we go through the course. For measuring forces in the United States, if you go to the grocery or go anywhere else, they talk about we measure forces in pounds. But in this class, we're going to measure forces in units called newtons. Notice that there's a lowercase n here, but in the abbreviation, we just use the standard of using the capital N. A pound is about 4.448 newtons, or a newton's about 0.2248 pounds. So a newton is about a quarter pounder. So if you go to the Big Mac and you grab one of those Big Macs, then you're eating about a newton. When you lift that up to your mouth, you can always think, that's it. I'm eating a newton pounder. Okay, never mind. Alrighty, so let's talk a little bit more about how we draw these. An arrow over a boldface symbol indicates that it is a vector. And a vector and a scalar are two different things. So whenever you see something that might be in bold or it has an arrow on top, we call that a vector. If something is what we call a scalar, then that will not have that arrow over the top. And typically what you'll see is you'll just see the abbreviation will be italicized and not bolded. And the big difference between a vector and a scalar is illustrated here in this slide. So a vector has what we call magnitude and direction. So if I am pushing to the right, let's say that I'm pushing this little figure here, so they're really happy to be pushed, and I push them in that direction, I can say that I push with 5 newtons, and I'm pushing that person to the right. I could also say that that would be to the east, to the right or east. If this is forward for him, I could also say that it's forward. So as long as I have a direction with my magnitude, then that is a vector. If I have something different called a scalar is a quantity that only has magnitude. So I don't have anything else with that. Speed, I'm going 5 meters per second, doesn't matter which direction. Time, 5 seconds. 5 kilograms. If I have a position and I haven't talked about where it is, I just say I am 25 kilometers and I'm at the 25 kilometer point. That is position. So vectors and scalars, really important that you know the difference between the two. For notating vectors, typically what we do, like we said, is we either use a bold capital letter or a lowercase letter sometimes, or we can just use this arrow on top, and that's how you draw a vector. So here this vector R is pointing up and to the right. It always has a tail and it has an arrowhead on it. If I do scalars, scalars are not in boldface type, okay? So sometimes it's hard to tell. So it's probably better to make sure that when it's a vector, we put the arrow above it, and when it's a scalar, we just draw it. And there's really no standard way to draw a scalar. The direction of vectors, you'll see that for this vector, it has an x direction, and it also has an angle, which means that we always want to think about that angle as the direction itself. Letter B here has a much bigger angle, and what we're basically doing here is using different ranges for our vectors. If you're in quadrant 1, so if you go back to your math days, and you're in this first quadrant, you're going to be anywhere from 0 degrees all the way up to 90 degrees. If you are in quadrant 2, it's going to be anywhere from 90 all the way to 180 degrees. Quadrant 3 will be 180 to 270, and then finally quadrant 4 will be 270 to 360. So we typically like to start at the positive x-axis, and then we just want to go counterclockwise. And when we do that, we can measure angles in terms of the numbers that you see here. We won't always do that, but that's one standard that you could use if you want to. The magnitude of a vector is really just the length of the vector. That length is proportional to the magnitude, and so if I want to look at this vector A, I have a displacement of 3 miles to the north. If I have B and it's twice as long, then we would say that that represents 6 miles. Now, because it is a vector, we're going to say up here is north, so you could think about if you had a map and you wanted north here, this would be south, and then we also have our east and our west. So you'll see them talk about vectors in terms of north, south, east, and west. You could also do up. This could be up. This could be down. This could be to the right, and then this could be to the left. So it doesn't matter how you tell about them typically, it's just that as long as you have some sort of direction if it's a vector. And the problems usually say what to do for those. Equal vectors. You'll notice that all of these vectors are exactly the same. Doesn't matter how many they are, they all have the same length and the same direction. And so we could say maybe these represent a force or a velocity. Inverse vectors are vectors that point in the opposite direction. So this one is A, we're going to say this one's negative A. Notice that the length of each one is the same, so that's the A part, but this one's pointing in the opposite direction. So that one gets a negative value since it's going in the opposite direction. This next section shows you how to resolve a vector into different components. So what do we mean by components? Well, we've got our vector A here, and there are two components. There is an x side that we have in terms of the length from left to right, and then there's also a length from the bottom up to the top, and we can represent those with a couple of different lines. So this would be our component of vector A in the x direction. So that's pretty easy to see. In order to solve for what this value is, I'm going to just simply take A, which is the length of my vector, times the cosine of the angle. So I need both the magnitude and I need the direction for that. This just basically comes from our good friend, the Pythagorean theorem, or just looking at how we do the angles here for a right triangle. So Pythagorean theorem says that basically this side, or the hypotenuse, is equal to the square root of the side that we see here, which we're going to call the x side, plus the square of the y. So if you do that, you'll end up with this side. But because we're dealing with components and we have an angle, we can make this a little bit better. We can say if I know what this side is, I can find either one of these two sides just by using trig. This is the hypotenuse of the triangle, so there's the right angle. We know that this is going to be the opposite side, and we know that this is going to be the adjacent side. So if you go back to trig, and let's say that you stub your toe walking into the room, what do you do with your toe? You soak, toa. So you want to soak your toe. That's the way I remember it. Makes it a little bit easier to know. So how does that make this? So here is our a to the x. This hypotenuse is really what we're calling A, and we want this adjacent side. So the adjacent here is cosine. Aha, that's where the cosine comes from. And typically what we'll do is we'll say that we know that the cosine of any angle here for this triangle is equal to the adjacent side, which is our a to the x, all over my hypotenuse. And our hypotenuse is really a. So now I can solve for a to the x, and that would just be a to the x is equal to a, which is the hypotenuse, times the cosine of the angle. So that's where that comes from. Let's go ahead and take a look at the y component. Works the same way, but instead of using cosine, we're going to use sine in this one. Oops, I'm going to back up again. We'll use sine in this one, and so we just know that the component in the y direction is equal to our vector times the sine of the angle for the direction of that vector, and still using that same triangle, that same right triangle. Looking at this one, same thing again. Here we go. We've got Rx and we've got Ry, and I know that this side would be R. You can solve for R either using the Pythagorean theorem, or you can simply just use the component method that we were talking about earlier. So here, if let's say I do know Ry and I know Rx, if I want to find the angle, there's a shortcut. I can just use trig, and the angle will just be the inverse tangent of whatever the y value is over the x value for that vector. And that just comes from the tangent of the angle is always equal to the opposite side over the adjacent side. And in our example here, our opposite side is Ry, our adjacent side is Rx. If I want to have the angle by itself, I have to divide both sides by tangent. When I do that, what will happen is I get the angle. Since my tangents go away, we're not worried about this, is equal to, now tangent 1 over tangent is really just the inverse tangent. So this is just the math where it comes from. It's not really important that you understand where that comes from. Just know that if you move it to the other side, if you move tangent, cosine, or sine to the other side, you need to make it an inverse. So that would be the inverse tangent of Ry over Rx. Always divide these first, then do the inverse tangent, and then that should give you an angle to work with. So that's finding the angle. If I want to find the magnitude, we can just basically use the Pythagorean theorem. So if I know Rx and I know a value for Ry, I can find R very easily. So this next part is just the graphical addition of vectors. If I want to add two vectors like A plus B and I want to make R, so here's A, and I'm going to add B, and I want to make R, I can simply I can do it a lot of different ways. This is called the head to tail method, so I just went I drew my vector and then I placed the tail of B at the head of A and then drew a line down, and if I'm done, then I just start at the butt end of letter A and I go to the head end of letter B. Back in the 80s on MTV there was a show called Beavis and Butthead, and that's how I remember butt to head for this. Kind of goofy, but that happens. R is what we call the resultant because I've added the two together. If I want to know what the equilibrium is, so if I sum two or more vectors, we do call that resultant. The resultant can replace the vectors from which I kind of took them from. And if the resultant is completely canceled out by adding its inverse, then we call that thing the equilibrant. So what is the equilibrant? Here's our resultant. If I want to get rid of this vector, I just need to subtract the opposite vector. And so here we're going to call it the equilibrant. Notice that the arrowhead is no longer on the yellow line. It is no longer pointing right, it's now pointing down to the left. So if I add E and R, I end up with nothing because they are equal and opposite in direction. For the next part, we'll do this in class a lot, so that'll help a little bit. But let's say that I have several vectors. I have A, B, and C. In order to find out what the overall value is when I sum the three vectors together, I can add up all of my x values and I can add up all my y values and make just a single x and y value. So that's essentially what this slide is saying. And then I can calculate the magnitude by taking the sum of all my x's and the sum of my y's, plugging it into the Pythagorean theorem, and that gives me my r value. And then I can use my inverse tangent again in order to find out what the angle is. A lot of this might not make sense until we actually do a problem, so let's go ahead and do a problem and see kind of what we get. This one's a little bit simpler to do. So if we're standing on the floor, we're doing our daily exercises. You lift your arms up until they are horizontal. In this position, we can assume that the deltoid muscle in your shoulder exerts a force of about 270 newtons at an angle of 15 degrees above the horizontal on the humerus. So here is our line going left to right. And notice that this one, even though our little picture here is going to the left, which we did not do before, we can look at both of our components. So there's our x component, and then our y component would start here and come down. So now we've got our x and y components for this picture. Let's go ahead and try to solve for those. So this gives you just a little bit about what we're trying to do and some of the strategies that we'll use. So I'll let you kind of read through those if you want to. And then here's a simplified picture. So we've taken the arm out with all the other things that are kind of in the way, and we do see that force in the x and we see the force in the y. So these are the two components that we were talking about earlier. In order to do this problem, the first thing I need to do is say, okay, I want to find out what is that force in the x direction. We said that the force in the x direction was equal to the overall force. So these are this is a component. Here's our vector. So that would be the force in the the force in the x direction. I'm going to make this absolute value is equal to the overall force times the cosine of 15 degrees. We also want to do the same thing in the y direction. So here in the y direction, we're going to say that the force of the y, absolute value, is equal to the force in the up direction times the sine of 15 degrees. Now the interesting thing here is we're going to have a little bit of an issue because we're going left. And so because we're going left, we're going to make this component negative. So anything to the left of the vertical axis is going to be negative. So our value for the force in the x direction should be negative. Let's go ahead and plug in. So this would be negative. We know that our overall force here was 270. I'm going to take that times the cosine of 15 degrees. And you want to make sure that your calculator is in degrees and not in radians. And when we're done, we're going to end up with negative 260 newtons for this vector. So this is negative 260. It's negative because it is pointing to the left. And our value of 260 comes from f times the cosine of 15. Let's do the same thing for our y direction. So here we're going to have, instead of negative 270, we're going to have positive 270 times the sine of 15 degrees. And when you do that math, you should end up with 70 newtons. In order to check this, simply what we could do is we could add these vectors back again together, and then we could do the y over the x using our inverse tangent feature, and we would find out exactly what that would be. So let's go ahead and do that next. So on this last slide, we're basically just going to check our answer, make sure we can kind of work backwards. So that overall force, again, the magnitude of the force, so we won't put the bar over it, is equal to that 260 newtons squared. So that was the force in the x plus 70 newtons squared. Here we're going to use the absolute value because the direction won't matter for our magnitude. When you're done, you do get 270 newtons. And then we need to find the angle and make sure it still is 15 degrees. So this is the inverse tangent of the force in the y over the force in the x. So this would be the inverse tangent of 70 over 270. And if you do that in your calculator and make sure it's in degrees, you will get 15 degrees. So that is our check. Moving along, if we go on to the next slide, here we've got a little bit more difficult problem. This one says an attraction apparatus. 3 cords pull on the central pulley, each with a magnitude of 22 newtons in the direction shown in the figure. They want to know what is the sum of the forces exerted on the central pulley by those 3 cords. And they also here want us to give the magnitude and the direction of the sum. So let's go ahead and go on. Oops, we're going to go on to the next slide, and we'll take a look if I can get this to work. There we go. So here it just says sketch the graphical addition of the three forces. So we see the three forces. We have two forces along that pulley because there's two ropes. So if we go back one more time here, two of the forces are in the same direction and they're pulling on the leg up to the right. The other force, the third force, is actually pulling down to the right, and we're just trying to keep that leg stabilized. So to look at in terms of the X and Y components, we're going to go ahead and use what we learned before. We'll notice that we have F1 and F2, and they're essentially the same. I don't like how they drew this. It really should be something that looks more like this, where you have an F1, and then you would also have maybe, I don't know, we could put another line here in red, which would also be pulling on it, and this red would be F2. But notice that both of these are the same essentially. So whatever we do with F1, we can just multiply it times 2, and that will give us both of those vectors. So let's go through and do this for the X. So we're going to do F1 of the X, which will also be F2 in the X direction, and then we're going to do F3 in the X direction. Notice that all three of those will be pointing in the same direction, so when we add them, they should just add up very easily. So in the X direction, we're going to say the force of number 1 in the X direction is equal to, and then we've got that force in the X direction of 22 newtons. So that'd be 22 newtons times the cosine of 45 degrees. And for F2x, that would also be 22 newtons times the cosine of 45 degrees. Now, I usually drop the units when I'm doing this just because there's already some letters in here and I don't want to get it any more confusing than what it probably is. So let's go ahead and figure out what 22 times the cosine of 45 is. So if I do 22 times the cosine of 45 in my calculator, I get about 15.56. So this one is equal to 15.56, and then this one's also equal to 15.56. I need to do this for the third force in the X direction, which is this one, and we only want what's going on here, so we're going to do 22 times the cosine of 30 degrees. And when I do 22 times the cosine of 30 degrees, I get about 19.05 newtons. I need to sum all these together, and that will tell me what the overall force is just going in the X direction from these three vectors. So if I add those up, I should get something close to somewhere around 50.16 newtons. Now that we've done this in the X direction, so that's the force sum of the forces in the X direction, we need to do it in the Y direction also. So let's look at F1y. We're going to do F2y. So there's F2y. And then finally our third force in the Y direction. So our first force in the Y direction we know is going to be 22 times the sine of 45 degrees. Our second one is also 22 times the sine of 45 degrees. And then our third one, notice it's pointing downward, and because it's below the y-axis, below the x-axis, this one needs to be negative, so it's going to be negative 22 times the sine of 30 degrees, and it's because now we're looking at this third one pointing down in that direction. 22 times the sine of 45 is actually the same as 22 times cosine of 45, so it's 15.56. This one is also 15.56, but watch out, this one's going to be negative, so this is going to be negative 11 newtons. So we're going to put 2 zeros there. If you add all these up, you should get somewhere around 20.11 newtons, and that would be the sum of the forces in the Y direction. To go back and let's just kind of see what the overall force will be for this thing. We know that the overall force should be equal to the sum of the square root of the sum of the squares, so that'd be the force in the X direction squared plus the force in the Y direction squared. That's equal to 50.16 squared plus 20.11 squared. And if you do that math, you'll end up with about 54 newtons. So now we know overall on this person's leg, we have a 54 Newton force. And that force, we're not sure what the direction is, but we know it's pointing somewhere up to the right. So let's put that in red. So I've got a 54 Newton force, and it's probably like this. So that's that's the overall force, 54 newtons. But we want to know, what is this angle right here? So to find the angle, we're just going to use our inverse tangent function again. So we'll say this is equal to the inverse tangent of the sum of the forces in the y over the sum of the forces in the x. So this is the inverse tangent of the sum of the forces in the in the y we said was 20.11, and then the x was 50.16. So we end up with 21.8 degrees. So our angle here is now 21.8 degrees. So that's the overall pull on that leg from the apparatus that we've got the leg up on. And so you can see there's our two numbers, our 20.11 and our 50.16. And we said that the overall value here then was about 54 newtons, and the angle here was about 21.8 degrees. And that's where we're going to stop for the first section of the notes.